How's it going today? So in this video we're going to be talking about the pressure volume curve, and we're going to be relating it to our four-chambered heart over here. So on this graph, on the y-axis, we're going to have our pressure, which is going to be in millimeters of mercury, and on our x-axis we're going to have our volume of blood, which is going to be in milliliters. And so we're only going to apply this graph to the left side of the heart because we know it's a two-pump heart. And so the right side's going to be a little different because it's going to have different pressure. But we really only care about the left side in this video. So let's start over here, point A. And at point A, I'm going to call this point A. So point A, we're going to be at 3 millimeters of mercury, 3 mmHg, and 50 milliliters of blood. So how does that relate over here to our four-chambered heart? Well, in our four-chambered heart, basically what that's saying is we're going to have 50 milliliters of blood in our left ventricle, and the pressure in that left ventricle is going to be at 3. And so we're going to have two different valves that are connected to the left ventricle. Over here we're going to have the bicuspid valve, also known as the mitral valve, and over here we're going to have the aortic valve. And so these two valves are going to be shut, which means no blood is going to be able to come in or leave. However, at point A is when our bicuspid valve is going to open. And so at point A, bicuspid valve opens. And so when our bicuspid valve opens, that's going to be this valve right here. And so that means all this blood that's coming in through the pulmonary vein, through the left atrium, is going to be able to come into the left ventricle and fill this left ventricle. However, this aortic valve is still going to be closed. So if we're filling that left ventricle, that's going to increase the volume of blood in there. And so what we're going to see here is a steady increase in our blood, and we're going to have a slight little increase in pressure at the end, and then we're going to get to point B. And so at point B, we're going to be at 120 milliliters of blood. And so when we get to that value, this bicuspid valve is going to shut. And you might be wondering, what's this little increase in pressure right over here? And so that's basically just going to be this left atrium going through its atrial contraction. So that little squeeze of muscle surrounding the left atrium is going to increase the pressure just a little bit as we get to point B. So we get to point B, our bicuspid valve now closes. So our bicuspid valve closes. And now we're sitting at 120 milliliters of blood in our left ventricle. Now remember that this blood coming back through the pulmonary vein is going to be oxygenated. Okay, so from point B to point C, and I'll draw it around here. From point B to point C, we're going to go through something known as isovolumetric contraction. And so isovolumetric contraction just means that our volume is going to be staying the same, so no blood is going to be coming in or leaving, but our muscle, which surrounds this left ventricle, is known as the myocardium. And this myocardium is composed of a bunch of sarcomeres, which look like this. And these sarcomeres are composed of actin and myosin filaments. And so when the brain tells the myocardium, hey, it's time to contract, this myocardium is going to squeeze together, which is going to squeeze this left ventricle. However, since both valves are going to be shut, if there's no change in volume, there's going to be an increase in pressure. So we're going to be increasing this pressure due to the squeezing of this myocardium. And that increase in pressure is going to be shown here. So we're going to have an increase in pressure even though our volume is staying the same. And so at point C, the aortic valve is going to open. And so the aortic valve is going to open when that pressure in the left ventricle becomes higher than the pressure in the aorta. And so at point C, we're going to see this thing known as systole, which looks like this. So this is known as ejection, which is also known as systole, and this is known as diastole down here. So from point C to point D, we're going to undergo something known as systole. Well, what does that mean? That's just saying that this aortic valve over here now opens, and so all this blood is going to go rushing through this aorta to the rest of the body. And so all this blood leaving this left ventricle is going to decrease our volume. And so from point C to point D, we're going to have a decrease in volume. And so at point D, that's going to be when the pressure in the aorta is equal to the pressure in the left ventricle. And so when those two pressures are in equilibrium, the aortic valve is now going to be able to close. And so the aortic valve is going to close. And when the aortic valve closes, there's going to be no change in volume for that left ventricle. And so to complete our graph from point D to point A, that's going to be something known as isovolumetric relaxation. Well, isovolumetric relaxation is saying that the volume is staying the same. However, now our myocardium is told, hey, now I can relax. So it's going to be stretching out, and that pressure is going to decrease in the left ventricle back down to 3 mmHg. And so that's going to complete our cycle, and that is how you relate our cardiac cycle to our 4-chambered heart.